welcome back. So today we're going to be taking a look at this pretty gnarly looking integral. This was sent to me by one of my former students, and he swears up and down that there is a solution that was given to him by a professor. So I'm going to take a crack at it and see what I can come up with and see if it is anything similar to the answer that he was given. So to begin with, this is the integral of 3x to the fifth power minus 3x squared plus x, all divided by x to the third minus 1 dx. And so this thing is a rational expression that is top heavy, i.e. the degree of the numerator is greater than the degree of the denominator. So this immediately makes me think that something like polynomial long division is probably the right move here. So I'll set that up. That's 3x to the fifth plus 0x to the fourth plus 0x to the third minus 3x to the second plus x plus 0, all divided by x to the third power plus 0x squared plus 0x plus minus 1. And it looks like the divisor's been cut off of the screen just a little bit. So all I did was I wrote x to the third minus 1, but I left spaces for the 0x squared and the 0x just to make sure that I don't miss anything during the long division step. This is one of the first things we're going to do. So we can see that we can create 3x to the fifth by multiplying x to the third by 3x squared. If we multiply x to the third minus 1 by 3x squared, we will end up with 3x to the fifth power plus 0x to the fourth power plus 0x to the third power minus 3x to the second power. And that's really nice because this whole thing just cancels down to 0, leaving us with 0 plus x plus 0. Which is, of course, unreducible by x to the third minus 1 because x is not a factor of x to the third minus 1. So we can rewrite this entire integral as the integral of 3x squared plus x divided by x to the third minus 1. So the next observation that we can make here is that x to the third minus 1 is a difference of cubes, which means that we can break it into factors. So that tells me that that part of this expression can be rewritten as a partial fraction. So we'll maybe rewrite this x over x to the third minus 1 term as a over x minus 1, which is the first factor in that partial fraction. And then we'll have an unreducible quadratic as a result of factoring the denominator. So that'll be bx plus c over x squared plus x plus 1. And we can verify that those are the correct factors by like the SOAP method or something like that. So now what I need to do is to determine what the constants for A, B, and C are going to be. And we have these undetermined constants right now. So we get that by just remembering that this whole numerator term actually has to equal to x, and that this denominator times this denominator is in fact our original denominator, x to the third minus 1, and then we'll do some like comparing of the coefficients. So if I do a common denominator procedure for this thing, I'll have ax squared plus ax plus a from multiplying a by the bottom right-hand denominator. And then I have to do this distributive action of bx plus c through x minus 1. So I have bx squared minus bx. Okay, and then I'll have plus cx minus c. And that is the distributed form of that thing. So next we notice since a, bx, and c, when I combine them in this fashion, have to reduce and cancel each other down so that I only have one x in the numerator of this term, I can combine the terms and do some like comparing of coefficients here. So the coefficients of x squared will be a plus b, and that's supposed to equal to 0 because there are no x squared terms in the original numerator. Next, I can compare the x's. So I have ax, negative bx, and cx, or in other words, a minus b plus c has to equal to 1 because I have precisely 1x in the numerator. And then lastly, I can take the constant terms, which is this a and this minus c, and notice that there is no constant in the original numerator, and so this is a minus c equal to 0. Next, I can solve this through like a reduced row echelon system of equations to determine what a, b, and c have to be. So I notice that I have 1a and 1b 0c's make 0. I have 1a negative 1b 1c makes 1. And then I have 1a 0b's negative 1c's makes 0. And I can just kind of go through the reduced row echelon method here to solve for what a, b, and c are once we've turned this coefficient matrix into the identity. Okay, so I'll just use some like row operations here. I notice that I can turn this term into a 0 by subtracting the first row from the second row once. That'll make that a 0, that a negative 2, that's a 0, that's a 0, so we're done. I can turn this one into a 0 by subtracting the first row once from it. So that's 1 minus 1 makes 0, 0 minus 1 makes negative 1, negative 1 minus 0, and 0 minus 0, so we're done there. Next, I can notice that on this bottom term here, it might be better to just swap the second row and the third row. And that's because I want to send this to 0, and I can't really do that with 2, but I can send 2 to 0 with 1 a couple of times. So I'll just move this entire row to the second row and this entire row to the third row. So this should actually say negative 2, positive 1. This should say negative 1, negative 1, and then of course the 1 and the 0 switch places here. So now I can also notice that this second row has negatives. So if I just multiply everything by negative 1, then that will fix the problem that I'm having there. I can now add the second row to the third row twice to turn this term into a 0, which will turn this term into a 3 and leave that term as a 1. Next, I can divide by 3 to solve for c. So if I divide by 3, that makes this a 1 and this a 1/3. Okay, next I can notice that I can turn this element here into a 0 by subtracting the third row once from it. So if I subtract the third row once, then that's a 0, and this is a negative 1/3. Noticing that the other two elements in that row don't change because the bottom row consists of a bunch of zeros. Then I can turn this element into a 0 by subtracting the second row once, which will turn this into a 0, and then subtracting negative 1/3 is like adding 1/3. So now I have results for what A, B, and C actually are. So A is supposed to be 1/3, B is supposed to be negative 1/3, and C is supposed to be 1/3, and that is our partial fraction decomposition for this thing. All right, I'm going to get rid of this here, and I'll just rewrite that whole thing so I can keep note of what I did there. And we know that A is a third, B is negative 1/3, and C is 1/3. Okay. So now we're ready to tackle part of this integral, and it looks like the part of this that's going to be the most difficult here is maybe this thing right here. And the reason for that is that I notice that I have a linear term over a quadratic term. So I'm probably going to have to do some kind of like splitting the fraction up so that I have some term that I can do maybe with something like a u substitution. It looks like I'm going to have to do a little work for that. And then something like 1 over x squared plus x plus 1. And I don't know how I'm going to handle that just yet. But let's just keep going and see if anything pops to mind. Okay, so we have the integral of 3x squared, which is, of course, just x to the third power. And then I have the integral of 1/3 over x minus 1. Well, if we constant multiple rule this out, we notice that what we have is a natural log derivative. And so that's just going to be the ln of the magnitude of x minus 1 all divided by 3. So that's actually going to be plus ln mag x minus 1 all divided by 3, and that takes care of this part. So then we have this thing over here. And I don't like the negative in particular in front of the x term in the numerator. So I'm actually going to factor out negative 1/3 as a constant multiple, which means we have minus 1/3 the integral of x minus 1 over x squared plus x plus 1 dx. Let me stop and think about that for just a second. So I think the right move here, we would really like for this to be like 2x plus 1 if at all possible. And I think we can do that because this is just x minus 1, so this actually isn't all that hard to transform into like 2x plus 1. And the reason that I'm saying 2x plus 1 is because if you notice the denominator term here, it's like x squared plus x plus 1. The derivative of that is 2x plus 1. So if I can get the numerator to say 2x plus 1, maybe by adding another fraction to it, then it'll just be a simple u substitution that will evaluate as the natural log of x squared plus x plus 1. And we don't include the absolute value bars in that because x squared plus x plus 1, I believe, is always positive. And I can check that here in a minute, but I'm pretty sure that it is always positive. Okay, so yes, it is always positive. The vertex of x squared plus x plus 1 happens at negative 1/2. And then plugging negative 1/2 in, we get 1/4 plus 1, which is 1.25 minus a half. So that will clearly be a positive number. So that's the lowest it ever goes. We don't need the absolute value bars on that. But I'm kind of getting ahead of myself because what I want to do is turn x minus 1 into 2x plus 1 if at all possible. But we can notice we can write x minus 1 equal to 1/2 times, and then this will have to say 2x to send that back to x, and this can be plus 1. That'll be a half. So I have to minus 3/2 on the end of that after that distribution. Those should evaluate to the same thing, which is x minus 1. So I can just replace x minus 1 in this particular integral with 1/2 of 2x plus 1 minus 3/2. But that's really nice because we notice that we have the precise derivative of x squared plus x plus 1 right here. And then I have this extra little thing added on to the end. But notice since the denominators of these two fractions are the same, that means that we can create the same type of fraction and just split this in half. So I think what we want to do here is to take this x minus 1 business, right, this is 1/3. So we'll have two distinct separate integrals here. We'll have 1/2 the integral of 2x plus 1 over x squared plus x plus 1. And then we'll have minus 3/2 the integral 1 over x squared plus x plus 1 dx. And I'll put the dx's on here. Okay. So that's really nice because now this integral is actually pretty trivial. We can just choose u to be x squared plus x plus 1, and that makes it 1 over u. That makes du 2x plus 1 dx, which is precisely the top. So that's just du over u, which is the natural logarithm integral. So I have 1/3 and a half there. That makes the total solution at this point x to the third plus ln mag x minus 1 all divided by 3 minus, and then we'll have the ln of x squared plus x plus 1 all divided by 6 minus 3/2 the integral of 1 over x squared plus x plus 1 dx. plus, excuse me, there's double negative right there. Okay, so now we have one part of this left, and arguably it's the worst part of it. And I think that the right answer here, whenever you see 1 over like a quadratic term, like some kind of irreducible quadratic, I'm not saying that this is always right, but I'm saying that I think it's going to work out nicely for us now. This should kind of make you think of like arctangent, for example. And the reason is if I can make this say 1 plus something all squared, then this will evaluate as the arctangent of something. And then we'll have some like other constants on there at the front that I don't know yet. But I think we can do that by like completing the square for that x squared plus x plus 1 thing. So completing the square, we take half of the b term, so that's half of 1, which is a half, and we square it, so that's a fourth. So I need a plus and minus 1/4. Well, minus 1/4 combined with plus 1 will actually make plus 3/4. So I can rewrite this whole thing as x plus 1/2 all squared plus 3/4. Yeah. Yeah, okay, so that's in the correct form. That's going to be an arctangent integral, I hope. We just have to do a few corrections here to make this look more like an arctangent integral. So I guess the next step here, I'm just going to kind of keep track of my substitutions over here on the side. We can set v equal x plus 1/2, which means that dv will be equal to dx, and that's great because the numerator is just 1 and dx, so this is precisely dv. Then the bottom part of this will be v squared, and then I have this plus 3/4, which is not good because I need that to say 1 plus v squared in order for it to be an arctangent integral. The other thing is I've actually written those two terms backwards from like the standard way of writing it, so I'm going to go ahead and take care of that at this point. What we'll do is we'll rewrite this entire denominator term as 3/4 plus v squared, and then remember dx is just dv, so we have 1 over 3/4 plus v squared in dv. Cool. So that's like an arctangent integral, but I need that 3/4 to be 1. So in order to do that, I'm just going to multiply the top and bottom by 4/3. Doing that makes this fraction cancel down to 1, and then it actually puts 4/3 in front of v squared, but I need something that can be completely, like by itself, squared so that I can replace it with another change of variables and turn it into like an arctangent. So I think the correct move there is to rewrite 4/3 v squared as 2 over square root of 3v all squared. And that allows me to declare like another variable, which is t, as 2 over square root of 3v, so that dt is equal to 2 over square root of 3v, dv, or dv is equal to root 3 over 2 dt. Okay, great. So let's clean this thing up a little bit more here. I'm sorry, that's 3 over 6. Yeah, that's 3 over 6. Okay, so what I'm noticing is that when I wrote this down, I wrote 3/2, and I did the double negative correctly, so that is plus. But what I didn't do is I didn't put the 3 also on bottom, which actually just means that this is actually 1/2 of that integral. So I apologize about that. Anyway, now we're ready to do the rest of this. So I can send this 4/3 out front as a constant multiple to make that 1. 4/3 times this is actually 4/6, which is 2/3. Okay, so then if I make this substitution here, then we notice that we also have to multiply this thing by a constant of square root 3/2. Well, the 2's will cancel there, making this actually the square root of 3/3. And now this is an arctangent integral. So this thing is going to work all the way down to x to the third plus ln mag x minus 1 on 3 minus ln of x squared plus x plus 1 on 6 plus, now notice that this is square root 3/3, which is the same thing as just dividing by the square root of 3. Let me get rid of these sets here so that I have a little bit of extra room to write. And this will end up being the arctan of something over the square root of 3. So what that something was, the key variable was 2 over square root 3 times v. So then notice that the original v variable was x plus 1/2. So that's actually 2x plus 1 all over square root of 3 plus c. Yeah. Yeah, I think that's right. Okay. So there's our answer. And I'll go back and I'll double check this with my document. Yeah, so I did go back and check the solution sent, and it turns out that this is out of order, but it is correct. They have this listed with this part first, and then this part in the middle, the x to the third right before the arctan. So like it doesn't. They're all linear, so it doesn't matter what order they're in. But all the parts are here. So yes, this is in fact the solution that they sent. So I am very happy with that. That was pretty nasty.